Now for example 2, we need to know what an objective function is. An objective function is find the best combination of values in order to maximize or minimize a certain function. This is very, very important when you do problems like these in the real world. We want to maximize the profit that we get, or we want to minimize the amount that we spend. That is often what they're used for. Okay, so we have solving linear programming. So one of Jillian's priorities for the greenhouse, or the green roof, is to help control air pollution. To do this, she wants to maximize the amount of carbon dioxide the plants on the roof absorb. Using carbon dioxide rates of absorption and the data from example 1A to find the number of each plant Jillian should plant. So we have these here, the blue lagoon sedum, which is 1.4 pounds of carbon dioxide a year, and the red raspberry is the 2.1 pounds of carbon dioxide per year. Okay, so we need to write our equation that we have. That's our first step. So write the objective function. So we have, you can call it anything, let's just call it C. Okay, we have to have our amount per blue plus our amount per red. So this is our objective function. 2, find all of the vertices. These are your corners. Vertices. So we have to go back to our graph. So here we go. Here's our graph. So all of our corners. So this point here, that is 0, 300. Our x is 0. Our y is 300. We have 0, 0 down here. We have, it connects here, so 400, 0. And then we've got 250, 150. So I'm going to write those back over here just so we can see them. We had 0, 300, 250, 150, 400, 0, and 0, 0. We want to, just said to maximize. That means I want the most. So plug in vertices into objective function. Okay, so we're going to plug them right in here. So if I plug this one in, I'm just going to grab my calculator and just do it all at once here. We have 1.4 times 0, because remember these are our blues and these are our reds, according to our graph, plus 2.1 times 300. When I plug that in, I get 630. So this one here is going to C equals 630. I'm going to do the same thing for all these. So 1.4 times 250 plus 2.1 times 150. I get 665. 1.4 times 400 plus 2.1 times 0, 560. This one's super easy. Anything times 0 plus anything times 0 is 0. If we want to maximize, we want to find which one is the biggest. Well, this one's the biggest here. Okay, so our maximum answer here is that we are going to have 250 of the blue and 150 of the red. This is our maximum answer. Now let's try for 1C here, or 2C, back to 1C. Yum's Bakery wants to maximize its profit from bread sales. One batch of A yields a profit of $40. One batch of B yields a profit of $30. Use the profit information in example 1C to find how many batches of each bread the bakery should make. So let's make our equation here. So we've got $40 per A plus $30 per B, and that is our profit. So we'll call it P this time. So now we have to go back to our graph, our vertices. We had 4 lines, so 4 vertices. 30, 15. We had 35, 0, 0, 0, and this one up here is 0, 45. So 0, 45, 0, 0, 35, 0, and 30, 15. Remember to take each one of these that we just found and plug it into here. Okay, and these were our A's and these were our B's. Okay, so 40 times 0 plus 30 times 45, plug it straight in a calculator. I get P is 1350. What? Anything times 0 plus anything times 0 is 0. Let's do the other one here. Sorry about the glare there. So 40 times, what is that? 35 plus 30 times 0. 1400. And now let's do our last one. 40 times 30 plus 30 times 15. So P is 1650. Okay. Now we wanted to, what did it say? It said to maximize, make it the biggest. So which one of these is the biggest? Well, the biggest one is this. So we want to sell 30 of bread A, so 30 of A and 15 of B. And that will maximize. I want you to try B. Maximize the objective function. And this time I gave it to you since it's not a word problem. P equals 25x plus 30y under the constraints from example 1b.